Hey everybody, my name's Jordan, and today we're going to be talking about the token sale lock script. On today's agenda, the first topic is prerequisites, what you're going to need to know to understand what we're going through. Then I'm going to do a brief introduction on the token sale lock script and explain how it's used. Then I'm going to do a code walkthrough where I actually show you the code and explain why certain things were done the way they were and the motivations behind them. Then I'm going to cover some improvements that could be made to the script, and I'm going to explain also why they were done the way they were for this demonstration. And lastly, I'm going to cover where you can get more help if you need it. Before we get started, you should be familiar with the Rust programming language. That is the language that this script is programmed in, and it's also the recommended language for designing smart contracts on the Nervos platform. You should also be familiar with the Capsule framework. This is the framework that was designed specifically for building smart contracts in Rust. And you should also be familiar with the cell model as well as the generator validator design pattern. These two together form the basis of how we form transactions on Nervos. And lastly, you should be familiar with the simple UDT standard, which is the ERC20 equivalent, but on Nervos. So, what is the token sale lock script actually for? It allows the on-chain automated sale of SUDD tokens for a set price in CK bytes. This makes it great for things like ICOs, but we didn't call it the ICO lock script because this is really a generalized script that can be used for any token sale purposes, not specifically for ICOs. And how is it used? It attaches to any SUT cell as the lock script, whereas normally you have a lock script that corresponds to one specific user, making them the effective owner. This one replaces that lock, and it unlocks for anybody who wants to buy SUD tokens at a specific set price by the developer. So the developer specifies the token price, and then the token sale lock script enforces that proper exchange rate on chain when they want to actually buy something. And in case you're wondering how users will interact with it, they'll probably go through a front end that is usually like a website or the typical Web3 type of interactions. So how are smart contract rules enforced? Enforcement is handled by three distinct rule sets. The first is the SUDT TypeScript, which enforces the conservation of tokens and forbids a user from minting tokens for free. The second is the Nervos CKB protocol itself, which enforces the conservation of CK bytes. And just like with SUDTs, it forbids the user from minting CK bytes for free. And lastly is the token sale lock script, which enforces the exchange of CK bytes for SUDT tokens in the context of a token sale cell. So on Nervos, it's actually sometimes the interaction of several scripts or protocols that really constitutes a full smart contract. And in this one specifically, the token sale lock script is designed to be very minimalistic in its scope of what it's concerned with. It's concerned with its own token sale cell, and anything else in the transaction it doesn't really care about. And this allows a very high level of batching. You could actually put in many transactions next to each other. And because they're only concerned with themselves within that transaction, they don't really affect each other and they can be effectively batched. What does a transaction look like? This is a pretty basic transaction here where John is going to purchase a small number of tokens from the token sale cell here. Now we want to pay attention closely to the numbers here. John has 110 capacity, which is the same as CK bytes. And token sale cell, they have capacity 100, SUDT tokens 1000, and it has a cost of 1, which means 1 CK byte per SUDT token. And if you look at the outputs, you can actually see what was happened here. See, John's capacity went from 110 to 100, while the capacity of the token cell went from 100 to 110. And then the SUD tokens went from 1000 to 990, and John gained 10 SUD tokens. So this token sale script itself enforces that the exchange rate was proper and that John actually paid the proper capacity for 10 SUD tokens. And since all of these numbers are in agreement here, this transaction would go through successfully. So next I'm going to take you into the code and explain some of the motivations behind it. We're going to start with the arg definition here. Arg stands for arguments, and these are provided to every single lock script and TypeScript. The first is the owner's lock script hash, which constitutes the first 32 bytes. This is going to tell the script who the owner is and who has administrative control. The second is the cost per token in CK byte Shannons. This represents the next 8 bytes. It's a 64-bit integer. And the third is a unique identifier for the token sale cell, which is a recommended length of 4 bytes. And I'll explain that later and why this is important. And the constraints, we're going to go through these one by one as we actually walk through the script. So first, we'll just go down the line here and we'll take a look here. This block of code here is basically just some boilerplate from Capsule. This is all important stuff, but you don't really need to change that. Next, we're importing the result, which is since we're in no standard mode, we can't actually use the normal standard implementation. But fortunately, most of the core constructs and structures are available within other libraries, including the core library. So we're using the result structure, which is exactly the same as the one in standard. And next, we're importing a bunch of entries from the CKB standard library, which is for syscalls and structures within CKB. This is a really important one. You're probably going to want to get familiar at least with the high-level module here, because this is used pretty extensively as the main way that your script is going to actually interact with the rest of the system. So first, we define a couple quick constants here. Cost amount length. This is the number of bytes that's required for a token cost amount. This, like I said before, this is a 64-bit integer, so it is 8 bytes. The lock hash length is it's a Blake 2B hash, so that's 32 bytes. The SUDT amount data length. SUDTs use a 128-bit number, so they actually take up 16 bytes instead of 8. And then the args length, this represents the minimum argument length that could be provided to our script. This is a combination of the lock hash length and the cost amount length, which is 40 bytes. And if you look above here, you'll see that the lock script hash and the cost actually constitute 40, and that's because the third one here, which I will cover later, is not technically a requirement and isn't actually counted. So then next we have the entry and default alligator. Again, these are basically just parts of the boilerplate and you don't need to touch those. And we're finally onto our program entry point here. So it returns an I8, which is the return code to the main system. Just with like most applications, 0 represents no error and anything else is some kind of an error. So we're going to take a look at the main function now, which is where our program really starts. So the first thing it does is it loads up the script. Load script loads the current lock script. That's the one that's executing right here. And out of that, we pull out the current arguments. And so the first step here is we want to verify the minimum length of arguments that was given. And all we're checking here is it at least the minimum argument length of 40 bytes. It could be larger, that's fine. If it's less than that, then we're going to throw an error and exit right away because that's a major problem. But if it's more than that, that's fine. It's a common pattern in designing of scripts in Nervos that you can actually, when there's a byte requirement for the data area or the arguments area, that if you allow more bytes than was specifically necessary, that's usually fine because those bytes are not actually used, and other scripts might actually use that data area for different reasons. So this right here, that constitutes the first constraint, which is the arguments must be equal or greater to 40 bytes in length. Next, we're going to check the owner mode. So this compares all of the lock script hashes in the source input, and it's looking for a specific hash. So the first thing it does here is it unpacks the arguments and converts them into bytes, and we do that so it's really easy to compare. And then here's an important one here. This is one of the high-level things from CKB standard. The query iter, it takes one of the high-level functions. In this case, it's load cell lock hash, and converts it into an iterator so that we can use Rust standard iterator methods to iterate over it. So what this is doing is this is pulling the lock hash out of every single cell which is in the input, and we're going to go ahead and use this function here, the find function. When this evaluates to true, it's going to return the first value and stop processing. So what's going on here is it's iterating through all of the lock hash values, and if it finds a lock hash, and if you note here, we're looking at the first 32 bytes of the arguments, but that's all we care about, the first 32 bytes. If that matches the lock hash of the cell, then we're going to return that it is owner mode. And the reason we're doing this is, as we said, we have to actually define a way that the developer can specify who owns the cell. So they put in as the arguments the first 32 bytes, which are the lock script hash that can unlock it. And then you see there's a couple different ways that you can really use many different ways to determine this. You could actually have something in the witness signature that would indicate that, but that would actually increase your cycle. So this is a pretty common pattern where what we do is we just look for any input cell that has already been unlocked with the proper credentials, because since that has to be done anyway, the VM already has to do all this checking to make sure that all the inputs are properly unlocked. If we find that one that was unlocked by the admin user, we can just go ahead and assume that it is proper, because the protocol itself is enforcing that security. So we don't need to check the witness. All we need to do is check the arguments. So next, let me go back up to the top here. This is the second constraint here has now been fulfilled by that. Okay, so next we validate the token sale inputs. So this checks the inputs to ensure there is a single input token sale cell. So this kind of goes in a little bit backwards order here. The first thing we do is we load what would be at index 1, which is the second cell. And what we're actually looking for is an error. So if it loads properly, then we actually throw an error. If it loads improperly, then we can go ahead and proceed. And the reason we're doing that is because we wanted to ensure that there's exactly one token sale cell, not more than one. So if there's 2 or more, then that's a problem, and we can detect that error right here. So one thing we want to pay attention to is the source here. We're looking at group input. For inputs, there's 2 different inputs. There's group input and there's regular input. Regular input will process every single cell in the transaction, while group input, in the context of a lock script, will only match other lock scripts which have the exact same lock script with the same arguments and everything. So we're just looking for cells that are exactly the same and have the same lock script and everything. Now, if you change the unique identifier here, that's technically a different lock script hash, which means that group input is not going to detect that. And so this is how we get around this. So if you wanted to create multiple cells that can actually do and batch them together, you actually have to have a different identifier. But for the purposes of this script here, we're using that identifier, whatever it is, to determine which cell is the cell we're concerned with. So we can really enforce that minimalistic viewpoint of we only want to be concerned with ourselves and not what else is in the transaction. So that's why we're ensuring that there's only one cell with that specific identifier on there. So the next thing we do is we load the cell itself from the group input. We're now doing index 0, which should always be successful since that's the actual script that's executing here. It should always be successful. And next we're going to extract the lock script and the type script from that cell. And if the TypeScript is actually optional, so if it doesn't have a TypeScript for some reason, we're going to fire out an error immediately and go ahead and quit. So assuming that everything has gone properly, we now have validated that there is a single input token cell, and that we have the lock script and TypeScript that are in use, and we can pass those to the next one, which is to validate the token sale outputs. And so this is going to ensure that we have a single token sale output cell now. We had one single input, we want one single output. And this creates a one-to-one comparison that we have to be able to determine when our values are correct later on in the script. So the first things we're doing here is we're just converting everything to byte slices just to make it easier to work with. And now we're going to loop through all of the output cells here and keep tracking with the one we're on. And we're also going to keep track of the ones that match our exact lock script and TypeScript, since that's all we're actually going to be concerned with, and we're going to count those up. So the first thing here is we load the cell. We're loading these from the output. Now, just like with the inputs, there's a source output and there's also a source group output. And it would be handy to be able to use group output here, but we can't actually do that because a lock script doesn't have a group output. It'll always be empty. If this was a TypeScript, you could use group output and it would be a little more efficient. But unfortunately, since we're doing a lock script, we have to rely on the full output, and this will grab every single cell in the transaction, output cell in the transaction. So there's no way to actually determine how many cells are in the transaction other than cycling through them. So what this is doing is we're just going to continue to loop through all of them, pulling out each cell value until we get this error here, the out of bounds error, which means we're at the end, in which case we break. And of course, just in case there's an error, we're going to go ahead and kick out if we hit an error. So while it's looping through here, it's going to be first, it's going to convert these to, just like up here, it's converting to byte slices, and then it's checking. It's checking the cell that we just loaded. Does it have a locking, the lock bytes, do they match the current lock script bytes? And the type bytes, do they match the current TypeScript bytes? And if we have one that matches, then we go ahead and increase that and count that. And so here's the actual enforcement here. We're making sure that we only have one because if you have more than one or less than one, there's a problem there. It means that something isn't being tracked properly and something's going to end up being out of balance later on. So now that we've done those two things, that should take care of constraint number 3, one input cell and one output cell that use the token lock script, and they must have the same arguments. And they must also have the same TypeScript. And the reason for them ensuring that they have the same TypeScript is because if they didn't have the same TypeScript, if you didn't actually check that, then you could technically swap in whatever you wanted, and you'd basically be able to rob them of all their SUDD tokens, and you could just put in what other script you wanted in there. You could drop in another SUDD token or whatever. So we definitely have to check the TypeScript and make sure it's the same between the two cells. Okay, so next we determine the capacity tokens and cost amounts. So determine cost amount here. The first thing we do is we unpack the arguments again just into bytes so they're easy to work with, and we allocate a buffer here, which is the cost amount length, which is 8 bytes, and this buffer will be used to actually read the data out, and we'll convert it to a 64-bit integer. So the slice start and slice end, we actually have to determine where in the arguments we're going to pull the data from. The first 32 bytes were the lock script hash, so our starts at the end of the lock script hash and it continues for 8 bytes. So here we copy out the data from the arguments to our buffer, and then we convert the buffer to a 64-bit integer, which is our token cost. And if the token cost is less than 1, then that's a problem. We throw out an error. We don't want to be giving out tokens for free. But as long as the price is 1 or greater, it should be successful. And this satisfies the 5th constraint, which is the cost of SUDTs and Shannons must be greater or equal to 1. Now we're going to determine the token sale cell amounts from the inputs and from the outputs. We're going to get the capacity and the token amounts. So before we jump into the actual function, you'll see we're pulling from the group input and we're pulling from the source output. So source group input and then just source output. Okay, so just like before, what we're doing here is we're creating some aliases here. We're making this a format we can use, and we're allocating a buffer to hold our SUDD amount data, which is a 16-bit. It's a U128. So we're going to loop through all of the cells in the source, and we're going to count up the capacity, and then we're going to count up the tokens. So just like before, we are loading the cell until all of the cells until we get an out of bound index. And then we're taking the cell, and again, we're converting it to byte slices so they're easy to work with, and we're comparing the lock script and TypeScript because all we're concerned with here is the ones that match. We're looking at other instances of the token sale lock script. So if you'll remember from the back in the main function, we loaded from group input and then just output. And this is similar to the previous steps, whereas group input's going to have just the lock that we care about. We verified that there was only one cell, so we're just processing that. And then output, we're going to have to go through everything again because we don't have the we can't use group output for a lock script. Okay, so the next thing we do is we ensure that the cell data is valid, and we do that by loading the cell data from the current cell, and we're checking that SUT data cell length. That should be 16 or more. Just like I mentioned earlier, the pattern, you can actually put in more data than the bare minimum. We're only concerned with the first 16 bytes, which constitute the length. So we just want to make sure that it's equal or greater than that. And assuming it is, we can copy that data out into our buffer, and we make sure that the SUT amount data length is exactly 16. So we're only copying out 16 bytes. If there are more, we're going to not pay attention to them. And then we convert that into a U128, and we add that to our current tokens. And then we also take the cell, and we pull out the capacity, unpack it, and we add that to our total capacity. And then we go ahead and return that. So in our main function, we did that with both the group input and the output. So now we have, for our single cell, we have one token sale cell that is on the inputs, and we found out the capacity and the token amount of that. We should have exactly one token sale cell output, and we've also found out the capacity and the tokens amount for that. So now we can take all of these, including the token cost, and we can validate these amounts to make sure that they all add up properly. So the first thing it checks is that the capacity must be more than the input capacity. The output capacity must be more than the input. This is because we're making a sale here. We're only doing one thing. We're taking in CK bytes. CK bytes will never be less in the output cell, though it should always be more. And this is enforcing that rule. And if it's at less than or equal, then we throw out the CK byte amount error. This takes care of the sixth constraint, which is the capacity and output must be always greater than the input. And where did token? Okay, let's go back to that. Okay, the next one is the output tokens must be less than the input tokens. And this is because we are selling tokens specifically. So if it's greater than, if somehow for some reason we gained tokens, that throws out an SUDT amount error. Because we are selling tokens, we are not buying back tokens for CKB. We only allow it to go one way. And this should satisfy the seventh rule, which is the SUDT amount of the output cell must be lower than the input cell. And the last rule here, the capacity received must properly equate to the tokens sold at the proper token cost. So this is a little bit of a complicated line here, but we take the output capacity and we subtract the input capacity. That gets us the difference. This is the amount of CK bytes that we gained in the cell. Then we take the input token amount and subtract the output token amount. And this difference gives us the amount of SUT tokens that were purchased. And so we take the amounts that was purchased and we multiply it by our cost, and we know exactly how many CK bytes it should have costed. So if these two are not equal, if this doesn't add up properly, then we could throw out an exchange rate error. There was some kind of an error made here. Now you'll see in a lot of different scripts, there's a common pattern, which is you would enforce that you didn't lose anything, but you would actually allow the sale of tokens for a specific amount, or if they wanted to overpay, you could allow them to overpay. We didn't do that here because this is kind of, we wanted to make it a little bit less error prone, just so it's easier for developers. If there's any kind of an error for any reason, it's going to kick it out. You can only buy it at the exact specified exchange rate. You can't overpay. And if your script has passed all of those rules, then it goes ahead and it kicks out a OK. which goes all the way back up here and sends out a 0 code, and your script is successful. So what could be improved? The first thing is probably cell optimization. In our example, we had several places in the code where we looped through all the cells, and with it, when we did that, we used the system called load cell to actually pull the cell data. Now, this is an expensive operation because this anytime you do a system call, it takes a lot more cycles than if you were just doing local operations. So you want to minimize those as much as possible. So we had several places in our code where we did a low cell or a load of something else, and you want to minimize those and do them only one time if possible. So there was definitely some room for optimization where we could have combined some of those loops and done more action in the loop itself, and only had to do one load cell instead of multiple. The reason that we left it the way it is because it was much more easy to read in its current form with the split up functions, and rather than combining everything into giant functions, which would ultimately be more efficient but harder to read. You'd probably also implement a minimum buy amount, which means that you must buy a specific number of tokens. You can't just buy one. And the reason that you would do something like this is basically to avoid denial of service attacks. Like if you were having a big ICO and somebody wanted to mess around, they could put in a massive amount of buy orders, which would kind of clog up all the live cells which are used. Every time that you have a transaction, you must have one live cell to dispense the tokens, and it can only be used by one person. After it's used as an input, it is no longer usable, and you have to use the new cell which is created in the outputs. So if you had a lot of people competing for those live cells to use in their inputs, they could kind of trip over each other. Now, realistically, you're not really going to hit that problem in most ICOs because it's going to be handled by a single interface, and you're not going to have too many people going directly to chain to try to do this. And also, you can create hundreds or even thousands of cells in preparation for a large ICO, which would really make it so there's not much of an effect. And that's why part of the reason for that unique identifiers is twofold, because you can actually your interface can actually identify the tokens and keep the cells and keep track of them, as well as the scripts being able to be batched together because they have different unique identifiers. So anyway, that minimum buy amount is something that we would probably include in a real production version. If your tokens are expensive, it's not going to be a problem. But if they're really cheap, then all of a sudden the door opens up for some kind of a denial of service attack. So we would also probably support tokens that cost less than 1 Shannon. So in our demonstration, the developer provides a cost in Shannons for a token, meaning that a token must be its cost must be at least 1 Shannon or more. If they wanted it to be less than 1 Shannon, then we'd have to change around our logic, and it would add some complexity to the script, which is why we left that out. But realistically, that is a function that you'd probably want in there because a SUDT is a 120-bit integer, while a CK byte is a 64-bit integer. And the reason that it's a 128 byte is because it allows an astronomically huge amount of tokens to be produced. And we wanted to leave the door open for the developers to have that flexibility. If they wanted to produce a just absolutely ginormous amount of tokens, they have that ability. And if they do that, they probably would have a very, very cheap cost per token, in which case they might cost much less than 1 Shannon. And that's also why you'd want to have that minimum buy amount in there again, because just in case, you take the precaution of trying to shut down anybody who wants to do a denial of service during your ICO. So if you have some additional questions or need some more help, we generally recommend that most people join our Discord server. We have the dev chat channel, which is for developer questions of any kind. And we also have the capsule channel, which is for capsule specific questions. We also have the Lumos and Polyjuice channels in there as well. So all of our tooling has a specific channel if you have those specific questions and you actually talk to some of the developers that actually created it. On Telegram, we have the Nervos Network CKB dev channel for those who prefer Telegram. And this is just a general channel for any topic, a developer topic, and it's not split up at all. Both of the Discord and the Telegram are staffed by the same people, so you can reach any one of us from either network. My name's Jordan. I'm available on Discord, Telegram, and Twitter. Feel free to reach out to me directly if you have any questions about this presentation or about Nervos in general. Thanks for watching.